Hello everyone, my name is Obi Nwosu and today I'll be presenting Lab 2. So these are just the table of contents, so we're going to first do the introduction and then data observations, and then the code, and the discussion, and then a conclusion. Okay, so the main principle in this lab is Coulomb's law, which tells us how electrical charges interact based on their magnitudes and the distance between them. In this experiment, we just use the tape model again, but instead of just observing attraction and repulsion, we analyze how the charges along the tape behave like clusters of point charges. The goal is to see how the distance and distribution of charge affect the overall electrical force. So, Coulomb's law states that the force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. In simpler terms, stronger charges in closer distances mean stronger forces. This principle is what governs the behavior of the tape strips when they're brought near each other. So in the model, the top tape was treated as a system, while the bottom tape acted as the surroundings. The tape had a mass of about 1.02 times 10 to the negative 4 kilograms, with a length of 0.15 meters and a width of 0.02 meters. So when we placed the two pieces of tape about 0.033 meters apart, they showed a slight repulsion, confirming that each carried charge. This is just a review of my code, and here's the model. So to simulate the interaction, we modeled a tape as like a point of, or as a cluster of point charges, and through the model and the code, we estimated um, the total charge should be around 1.73 times 10 to the negative 8 coulombs. Um, but if instead we treated the tapes as single point charges, the estimated charge came out lower, 1.01 times 10 to the negative 8 coulombs. The difference highlights that the way charges are distributed along the tape really matters. Distance and distribution both affect the net forces. So why do the numbers differ? Well, with point charges, all the charge is concentrated in one spot, which exaggerates the force. But with line charges, the charge is spread across the tape, meaning parts of the tape are farther from each other. This leads to weaker net forces compared to two-point charges. It shows how Coulomb's law depends not only on how much charge there is, but also on how that charge is arranged. So to wrap up, this lab demonstrated that neutral objects can polarize and that the distribution of charge plays a big role in how electrical forces act. By modeling the tape as clusters of charges, we saw more realistic behavior compared to assuming them as simple point charges. This helps us better understand how Coulomb's law applies to real systems, not just idealized ones.